Thank you so much. Okay, so it's mainly that I have a work on like so many different like the robot application for like the medical application. So, but somehow I just really wanted to show the how to really commercialize your like some research idea into real application. Because like no matter how do you work, research a lot, if you cannot just really sell this product in the end, then what is really point? I know though like the research is also really important, but somehow in this like my presentation, you're going to like to see how I just successfully really commercialize my research idea into the real application. Okay, so first anyway, like here's and then before I starting my presentation, like before and then I came to London and then I work on some here, so medical training system. For example, like we can't just really like conduct any like the experiment with the actual like the patient or actual people. Why? Because there is some ethic issue. For that reason, we made this robot patient. So the novice doctor or nurse practice with this robot patient. It was my like the first like my study in Japan, and after then I made this like the robot assist like ultrasonic diagnostic like the system using robot. Okay, and this is also one of like the surgical tool for like surgical operation like in our body. But somehow here's and then I'm going to present how I developed some sensor. You know those sensor. Now the AI is very popular, right? AI is always implemented into software robot. However, AI also needs some information, right? No matter how you are surfing internet using smartphone, all your users' information is AI eventually used all your information, and then they normally identify your character. But somehow, robot also really need some information. Why? Sometimes and then some people just say anyway, heat robot, or robot is also like the watching by eyes. Then they need some vision information, right? However, how the robot is interact with the object or human being at the times, and then robot may hit, right? People at the times, and then maybe people may be injured by the robot arm. For that reason, always robot arm need force and torque sensor. Okay, so somehow I'm going to show some sensor which can measure any physical quantity, right? To just really, but the older nowadays sensors are using for the robot application. Let's see like this is one of four sensor. Okay, let's see here. Now, maybe patient may not just really stand up himself. This is vision. The robot is anyway supporting like this patient right see here. Okay, so this case and then oh my God, here, yeah, this is my colleague, my friend, almost like 20 years ago, and then my Japanese colleague. So he has some abnormal over his mandible. For that reason, now the robot is anyway doing some massage, you know, around his like the mandible. But at the time, just imagine if we do not know whether robot like apply the really excessive force to the human being at the times, and then maybe human being may be hurted by the robot arm. So in this case, and then here, force sensor, this multi-axis force sensor are implemented to protect patient. And also, robot arm always keep same force, not to just really apply the excessive force. Why? Not to really hurt patient. Let's see like this one. Robot assist to like the ultrasonic diagnostic system, and then this ultrasonic, observe like the baby in the female's abdomen. At the times, and also same. Too much like this probe is applied on the female's belly. At the times, and the female may feel very hurted. For that reason, always also maybe robot arm just anyway apply the excessive force to the female pregnant lady. At the times, and maybe female may be damaged. For that reason, always we need to attach to this kind of force sensor for any robot application. What about this case? His first case. Robot is a hit. The this dummy is anyway, head is anyway broken, but now here, oh, how we can just really make sure the robot has some very flexibility. Now let's see here. First one is, oh my God, the guy is anyway, the neck is broken. However, second case, and then robot itself has some softness. In this case, and then using force sensor, also we can making the robot is softer. This is really important. Later, and then, like I'm not gonna really explain some impedance control. Impedance control means somehow we can making all the robot joint very softer. This is also one of the robot control. So for that reason, we need anyway force sensor. This is all. Have you ever heard of the strain gauge? Strain gauge, right? So you guys is anyway studying in electrical engineering. This is why you know that it's a strain gauge, right? The strain gauge, I really love this sensing unit because it is very reliable. To be honest, I have never seen any a sensing unit like strain gauge. I mean, there are a bunch of a sensing sensor to measure some deformation. However, strain gauge is the best. I mean, so far, okay? So the concept is very simple, right? Here. Okay, maybe here. So here, you anyway attach the top strain gauge one and another one. And then from this and then, when force is applied, then now we can see here, upper strain gauge is anyway expanded. And then the bottom the strain gauge is anyway contracted. For that reason, this is like the piston bridges. And then we normally can get this voltage out from this two strain gauge. So somehow now we increasing force, then this voltage out is proportionally increased. From this principle, once we know this voltage, once we know this voltage output, then we can find how much the external forces was applied. You understand what I'm saying? So this is very good. Most of the force and torque sensor designed based on the strain gauge. Okay, first, the merit advantage, high precision force and torque measurement, and high frequency response. High frequency response means now robot is anyway apply the 1 kilohertz input. At the times and then strain gauge respond against this 1000 hertz input. Most of the sensor cannot really guarantee more than 1 kilohertz. Most of the force and torque sensor, for example, magnetic and Hall sensor based force and torque sensor can guarantee maybe up to 100 hertz. The meaning is that we can't using that sensor so many application which is really require more than 1000 hertz any motion. Okay? So, and also here, reliability. Okay, sorry. This reliability means no matter how you purchase this force sensor now, but in 10 years and 20 years, 30 years, and then sensor always guarantees the same value. Do you understand what I'm saying? The sensor itself never be easily degrade. So once you purchase this one, and then in 50 years, and then sensor still okay. That is best. But cons anyway, demerit. Very expensive. And then noise and sensitive to the temperature. The meaning is that if you're using this sensor to some very cold location, and then maybe you may using this sensor to the very warm the country at the times, and then sensor value slightly change. But most of the sensor is very sensitive to the temperature. Not only strain gauge, but also other sensor has all this temperature issue. But that reason this is not really a big issue. So, and then the most problem is that it's really hard to fabricate. How? Let's see. You see here. We have to attach the strain gauge manually on the surface of a compliant mechanical structure. So we have to really attach the single strain gauge one by one. This is really, really time consuming, and then no matter how the you anyway attach to this like the strain gauge, but sometimes it may not work. So then you have to remove and then you reattach. So this is kind of really time consuming. That's the reason it's very expensive. Like 1 unit is a cost around 8,000 pounds. Maybe the euro, maybe 9,000 or 10,000 euro. How can you using like some force sensor with this 10,000 euro? But it's also sometimes quite easily broken. Like, then you have to, no, there is no repair. You have to buy the new one, okay? That's the reason like that somehow I just wanted to find something new approaches to design maybe new force and torque sensor using this optoelectronic sensor. I think that you guys know this optoelectronic sensor, right? LED and then put a transistor, right? I think here, smartphone also same. When you close to your eyes to our ear, then smartphone like the light is suddenly off. So most of the smartphone, so quite this like the optoelectronic sensors are very common in daily life application. But this optoelectronic sensor consists of a emitter and then detector. Emitter means kind of LED, light emitting diode. Okay, so this is anyway light source, and then now there's an object. Then here the light is emitted from this LED, and now the reflected light is transmitted to the detector. So then now this combination of emitter and detector, so-called phototransistor, can detect whether the object exists or not. Okay, but also another case, and then here this is a LED, and the other one is a detector, phototransistor. Then here also same. In this case also, this combination of these two electronic units can detect whether object exists or not, right? Here, first anyway, emitters anyway transmit all the light from the emitter is transmitted to the detector. Then at the times then no object. However, if there is object here, then no light is anyway received to the detector. For that reason, we only know the 0 and 1 condition, right? The binary condition. However, let's try to measure some very accurate distance. So now here, this is target, and then now this is a optoelectronic sensor, consists of a LED and phototransistor. In this case, and then here's and then there's some assumption. Reflector, there's no angle. Okay, so we just assuming here this emitters and then like the detector is in parallel with the target or object. So object is anyway flat surface. In this case, and then this optoelectronic sensor consisting of the LED and phototransistor can really measure very accurate distance. Okay, so here, for example, in this case, okay, so before and then like most of this optoelectronic application is to detect 1 and 0 condition, but now we just really wanted to detect in the very, very precise distance. That is our starting point, how to really design force and torque sensor. Okay, it's very easy. I think that right after this like the presentation, you can also making the low-cost 6-axis sensor, and then you can try. It is really working. So now here you have to really see why there's two like the measurable range area. Okay, you can see the one measurable area is purple. I think maybe this is like the red color. This is like the very short range of like the measurement, and the other one is the other one is purple area. So this sensor can measure very tiny distance ranging from 0.05 to 1 milli, no, 0.05 to 0.1 milli. And then the other like the distance measurement ranges are from 1 to 5 milli, okay? So in this case, and then here, in combination of this R1, R2s and N, we also like the tuned different like the measurement range. For example, here, something this purple ranges are, we can expand these purple ranges are a little bit larger, okay? Or maybe here, long range, here this purple color is also, depending on this resistance value, R1, R2s and N, we can optimize the measurement range, making the measurement range very shorter, or also we can measure measurement ranges are larger. This is somehow the very important parameter. So this presentation, and then first anyway, I'm going to show this short measurement range for force and torque sensor, and then later I'm going to show this long measurement ranges 1 to 5 milli for shape sensor. Okay. So first, how to estimate external force. For example, here, there's some cantilever beam, okay, beam, mechanical structure. I think is there any mechanical engineering student here? Cantilever beam. Cantilever beam is something like the structure looks like this, and then now here, when external force is applied here, then beam is deflected, right? You understand what I'm saying? But then now we attach this optoelectronic sensor to on the bottom of this, under the cantilever beam. So now when external force is applied, and then the beam is deflected, and then now this optoelectronic sensor can measure this tiny displacement, deflection. So then once we know the Young's modulus, right? Young's modulus of this cantilever beam, then now this D is a deflection, the amount of deflection. Then now when we know the deflection can be measured by this optoelectronic sensor voltage. For that reason, somehow we know the voltage, this output of the voltage of this optoelectronic sensor, and we know this spring coefficient. Then eventually we can estimate external force. That's the very simple concept, okay? So somehow here, very cheap. It's like this optoelectronic sensor is maybe 20p or 30p, okay? And then simple fabrication. Why? We just anyway mounted this optoelectronic sensor under any mechanical compliant mechanical structure. And then this sensor doesn't really require any amplifier. For that reason, no amplifiers, and then we just anyway mount this sensor under any compliant mechanical structure. It's very easy. So the meaning is that we can fabricate this sensor in mass production. So we don't really have to test by hand. Why? Later, using PCB, we anyway mount a bunch of this optoelectronic sensor, and we just anyway put this PCB, and then that's all. So we can really making the sensor in massive production. But the problem is that poor reliability and poor linearity. You can see here. This orangey color curve is anyway very linear curve. But somehow this output of this optoelectronic sensor showed some nonlinear curve. Okay? This is somehow I'm just really solving how to make this nonlinear curve to the linear curve. So this is currently what I'm doing at Brunel. And here is poor reliability. Poor reliability meaning is that I have never really tested this force sensor for 10 years and 20 years, 30 years. So who knows this LED or maybe phototransistor, right? This optoelectronic sensor consists of the two electric unit, LED and phototransistor. However, in 10 years, in 5 years, and then I do not know whether this sensor really showed the same performance or not. But I mentioned strain gauge one. Strain gauge is some scientists really tested this strain gauge for over 20, over 30, over 40. For that reason, strain gauge-based force sensor has a very good reliability. However, currently, this optoelectronic sensor-based force and torque sensor, nobody really tested this reliability for more than maybe 5 years or 6 years. Not yet. So this is somehow these days you can purchase a bunch of force and torque sensor using magnet Hall sensor. They're also same. None of them really tested this long period of the performance. Okay. So then now here. So this is a very common conventional 6-axis force and torque sensor. And then now it's here. They're compliant mechanical structures, and then every this lag, and then here there are a lot of these strain gauges are mounted on the surface of this compliant mechanical structure. Because strain gauges only measure deformation. This is why we need to attach that. This is on the surface of any material. So, however, I cannot just really for example, optoelectronic sensor. Optoelectronic sensor can measure displacement, not deformation. You remember here. It is just measure the displacement, deflection, not deformation. However, from the displacement, somehow, we can estimate deformation, right? So in this case, and then here, now this is a very conventional 6-axis compliant mechanical structure. However, I had to just really modify this structure to mount this optoelectronic sensor. For that reason here, previously all this leg, like this way, we attached the strain gauge on the surface of this each leg, but now all this each leg had to be just really modified into this cantilever beam structure. Cantilever beam structure like this way, okay? And then now here mounted this optoelectronic sensor, and then also I mounted reflector, mirror, reflector, okay? So then now when force Fx, Fy, Fz, and then moment 3-component Mx, My, Mz is applied on the top plate of this compliant mechanical structure, then all the forces are transmitted to the every leg. Okay? From this force information, we can calculate 3 moment component and then 3 force component. Here, same. All the forces anyway transmit to the each leg, and then now somehow this optoelectronic sensor can measure tiny displacement. From displacement, we can calculate all each leg force transmit from the top plate. Okay? From the that force information, eventually 3 force and then 3 moment can be calculated. This is somehow how to really design low-cost force and torque sensor using optoelectronic sensor. And now see let's compare the performance of this sensor. Okay. So actually I designed this sensor for this ultrasonic, robot-assisted ultrasonic diagnostic system, right? You see the movie clip. And then the blue color one is ATI one. It is roughly 10,000 euro, okay? And then my one is maybe 300 pound, meaning is roughly 400 euro, okay? Now we can see here. Of course, the 10,000 euro one is much better than my one. However, at least if I sell my sensor for maybe 1,000 euro, but that's not bad really quality, you know what I'm saying? So you can see here, reflector, and here's an optoelectronic sensor. Optoelectronic sensor, reflector, optoelectronic sensor, reflectors, and then each leg is anyway can measuring this tiny displacement, okay? So this is another version. nano 17, like the 1,000 euro one, small size one. Okay, this is a really, really famous force and torque sensor everywhere. So I think that like the, all the like this robotics, like, academics using this nano, right? The ATI, like American version one. Unfortunately, the ATI is the USA company, manufacturer is anyway USA one, and then I know that like the European before that in Hungary or Denmark also like they are releasing they have released several force and torque sensors, but the American version is accuracy is really, really good. Like for example, European one is maybe like error is maybe plus minus 3%, but the American one is maybe the error is maybe the plus minus maybe the like 1%. For that reason, the quality is really good, but very expensive. Okay, and also sensor is quite fragile. If you dropped it, the sensor on the ground, and then the sensor is broken, then you have to buy the new one. Okay, no repair. Remember, no repair. You have to buy another one. So somehow, this is to see here. Now you guys just see how this force and torque sensor has been really designed using the different the sensing element. Okay, optoelectronic sensor. And then here's my question is that why did you making this force and torque sensor? Why? Just you have to really remember why I designed this force and torque sensor so far. Because here, this is in Japan. I designed this the patient robot. Okay, patient robot. So in patient robot, we anyway integrated a lot of sensor inside. Okay, do you know the track intubation? Track intubation. When someone is anyway surgery, at the time the medical doctor injected some anesthetic. At the time, the patient is anyway sleep. Right? They're gonna be unconscious at the time. The medical doctor inserts some tube to the airway to providing oxygen before the surgery. Right? So at the times there are a bunch of side effects after this, track intubation. For example, some tooth is anyway broken, and here some the membrane, mucous membrane the trauma, and here some phalange also hurted by the tube, and then also tooth is anyway broken, and then so after this track intubation, after surgery, many the patient complain about some this side effect. But there isn't somehow using this patient robot, and then the medical doctors and the novice doctor practice with this the robot patient not to just really hurt damages patient organ. That is the main purpose. Why? We can't just anyway practice with the actual human being. That is the ethic issue. Who knows maybe your training may causes some permanent the complication of this patient, then who's gonna pay all this the compensation to the patient, right? So here's but here's how many sensors are integrated into this patient robot? Roughly 44 sensors inside. Okay? But then just imagine, company, we are selling this device, this patient robot is roughly the 20,000 euro, okay? 20,000 euro. But then each force sensor, the nano 17, the American one, maybe each one is the 10,000 euro, then multiply 40. How much we can, then eventually this machine, including the American version force sensor 40, then cost is gonna be at least to the basic cost is more than 20 euro, no, 10,000 euro multiply 40, and then 400,000 euro. And plus maybe company sell this one maybe 500,000 euro. Nobody really purchased this machine, right? That's the reason the company asked my previous university to design some force and torque sensor for this machine. Okay, so then now maybe each one is maybe 100 or maybe 50 pounds. Then 50 pounds multiply 40. Then it's gonna be maybe 2,500 euro, right? And then plus maybe company fabricate this patient model. Then we can sell this is anyway the 25,000 euro, okay? Including all these force sensors. Why? Because a company fabricating force and torque sensor, this is why we don't really have to this force and torque sensor expensive to the American company. So here, let's see another reason. Do you remember this one? Why the force sensor was used to this patient robot? You see here, before you saw the robot, force sensor, force sensor, first case, and then the robot anyway hit the human's neck at the times, and the human neck was broken. But here, we can also making the robot arm, robot quite softer. So every robot joint, we can making the robot joint like the softer. So then here's and then using all the joint, and then like the force and torque sensors are integrated into every joint of this patient robot, and then the impedance control, which is can making all the robot joint softer, are embedded into this patient robot. So for the reason, see here, when we apply the force at the time, you can see here, first, now when apply the 10 Newton at the times, and then the neck is like rotated 10 degree, for second case, and then now the 45 degrees. Somehow, we can making the robot joint some spring and damper model. So this is somehow, once you anyway study more, some impedance control, how to really making the robot joint softer, so at the times, and then you'll find. So meaning is that somehow using the force sensor, we made a robot some muscle stiffness. Okay, let's see one of the example is that before we injected anesthetic at the times, and then the muscle is all very stiff. Okay, so meaning is that you just anyway try to rotate the humans the head, it cannot easily rotate. However, after anesthetic, and then all the muscles are relaxed, and then you can easily rotate the human head. And also here, when you anyway lift the tongue by this medical device at the times, and then after injecting this anesthetic, and then before injecting this anesthetic, and then the muscle stiffness is totally different. After injecting this anesthetic, and then we easily lift the tongue, okay, by the special the medical device. So anyway, this is I designed this this patient. The patient robot is started from the 2007, and then this project ended the 2013. So now everywhere you can see this the patient robot, every hospital. Okay, so one day, and then you visit and then hospitals, and then if you find this, and then just remember my name. Okay. So then here, somehow this is summary. Low cost, and then easy, the fast manufacturing process, and also this optoelectronic sensor also can guarantee faster frequency response exceeding 10 kHz. But the limitation is that poor linearity and poor reliability. Okay, and then ongoing work is that. Then here, how to just really overcome this poor linearity. So this is why I'm using many optoelectronic sensor. You understand what I'm saying? Before, the cantilever beam is I only using one, right? But I'm going to using the many to just really detecting the more accurate displacement. But somehow I'm 100% sure that the accuracy is gonna be more increased. Okay, and then here another issue is that designing this compliant mechanical structure with a different material. This is also one of the big challenges. Okay. So here's I showed you how to design the force and torque sensor. Now the second chapter is that I'm gonna show how to really measure shape. Okay, shape. So roughly I can show you this shape within 20 minutes. So now see here, optoelectronic sensor here, okay? And then now we a little bit change this reflector shape. okay? The various radii of a reflective surface, okay? So here, most of the times, and then like there's some rotation axis at the times, and then see here. This is anyway circle, constant circle. However, we slowly, slightly change the radius. Radius is slightly increased, right? At the time, you can see here. Now this is we anyway fixed optoelectric sensor. Then now this optoelectric sensor measuring distance, right? Between surface and optoelectric sensor. So meaning is that from this way, somehow optoelectric sensor measure rotational angle, right? Because like that, we can map between angle to this distance. Then eventually, once we know the distance measured by this optoelectric sensor, then we can reversely measure rotational angle. So from this concept, now see here, maybe there's some robot joint, and then we here, robot fingertips, and then we mounted this optoelectric sensor, and then now we design here this surface, and then we design this like the curved, not constant like the radius, and then radius is anyway a little bit slowly increased. Then now you can see the like the optoelectric sensor can measure distance between this surface and this optoelectric sensor. From this measurement, displacement measurement, this sensor also can measure rotational angle. So here, so this is see here. So most of this is anyway the circle, and then now we anyway slightly change this like the reflective surface here a little bit radius anyway increased. Why? To just really measure this optoelectric sensor to measure this distance. Okay, so in this ways, and then somehow we can making some very low cost encoder. Okay, so there's an optical encoder. You know what I'm saying? Optical encoder. However, somehow in this way we can measure some angle. So then here, maybe there's some like the 5 different profile. For example, at the time maybe surface 1 case, and then something here. Now that this curved, this like the this curved like the surface anyway, from the 0 degree to 200 degrees, and then this radius anyway slowly, smoothly increased by maybe 2 milli. Okay, from the 0 angle to 200 angle. Another like the surface 2 case, and then something here is starting from 0 and then to the like the 180 degrees, and then suddenly here the radius anyway slowly decreased by 1.5 milli. From in this case, and then here we can this ways, and then we can measure different like the measurement range. For example, here this case, and then surface 1 case, and then here surface 1 yellow graph, something measurement ranges are roughly 200. Now here surface 2 case, and then the green one is measurement ranges are around 180, and blue one is surface 3s, and then this one is 140. The purple one is surface 4. Here starting from 0 to 120 degree at the times, and then here the radius is slowly decreased by 1.5 milli. Then optoelectric sensor can measure this distance, right? From this distance, reversely, joint angle can be measured. This is one of like the simple encoder. But here's an end. There's some question. There's a really good quality encoder. Why are you using like this like the stupid way to measure like angle? Have never really thought about this question, because like, there are a bunch of good encoder. Then why we are doing? Why we just try to measure all this like the angle with this optoelectric sensor? You may just anyway feel some questionable about this work, because like here something this is like the later you find. We first anyway really wanted to design some shape sensor. However, before we directly like the design shape sensors, and then first anyway, we just wanted to test like how this optoelectronic sensor can really measure rotational angle. So for example here, let's consider like this is a one-dimensional some link right here, and then now link, and then here we attach the optoelectronic sensor, and here also another link, and then we also attach this optoelectronic sensor. Then somehow we really wanted to measure some one-dimensional shape. Okay, why? Now this sensor can measure this link's angle. This sensor can measure this link's angle. This optoelectronic sensor can also measure this blue link angle. So then, somehow, we anyway put together serially. Then, somehow, this link, right? This series of link may measure very complicated shape. So, let's see here. For example, see here, then now see here. Yeah. So, each link has a surface, okay, curved surface, and also optoelectronic sensor. So then now you can see here, yeah, you can measure shape. So once you know all of this joint angle, and then you anyway put together, and then we can anyway visualize some very complicated shape. Let's see it this way. So then, now we anyway verified our first approaches, because like somehow we anyway using this curved like the surface, right, which has not the same radius, and then radius anyway slowly increased or slowly decreased, right? We used that surface reflector, and then we have really verified a one-dimensional shape. Okay. So it doesn't matter some manipulator is consists of a lot of this series of a link, but in this way we can anyway identify some complicated shape, right? But let's retry the three-dimensional case. Okay, three-dimensional case in it. This is you can see the left one. This is the conventional the medical instrument, okay, medical instrument, but the problem is that you can see this conventional instrument is their tool is just really the rigid structures, and then sometimes this medical tool may just anyway hurt organ. Why? Because the flexibility of this the medical instrument is very limited. Workspace is very limited. For that reason, sometimes this medical device cannot easily go inside. Or maybe this is the conventional, the conventional instrument may not just really go inside some narrow opening or limit space. For that reason, now that these days, a lot of scientists have developed the continuum flexible robot as a medical device. Okay, so then medical devices look like this continuum flexible robot. This is in general here. One segment is consists of the several unit. Another segment is also consists of the several unit, and then each segment is pulled by the 3 and 4 wires, and then the motor is always mounted remotely, out of this the manipulator, and then here another one is also additionally we pull the 3 and 4 wire, and all the motor is anyway remotely installed. It's quite remotely. So then here's we can really making the very complicated shape of this flexible manipulator. But however, the most current, this is a quite current issue, research issue in the world. For example, have you ever using the 6-axis robot arm? Yes. Then each joint have a encoder. For that reason, once we know the encoder, then we can reconstruct this encoder information to the like the robot geometry. This is very simple, right? Here's anyway we assume robot link is anyway rigid. If the robot link is not rigid, using encoded information, we cannot reconstruct like the robot geometry, impossible. But now see here, the problem is that now this flexible manipulator anyway go inside to the like in our belly, right? But at times and then, let's see the like the some, this is anyway here. Using, we pull the wire, then the flexible manipulator shape is like this kind of shape. But inside, in our like the bodies, and then some external forces apply in this direction at the times, and then robot shape is suddenly changed. So for example, like the no matter how you anyway order robot to anyway move to that like the way, at the times and then robot shape is not the same as theoretically. Actual robot shape in our body and then just theoretical. Theoretical, like when you anyway pull the wire, then you roughly know the right the robot shape, but that theoretical robot shape and actual robot shapes are not the same in our body. Why? Because there is no any close like the position feedback sensor inside. The most of a robot arm, right? You can you can easily read like the encoded information. However, this kind of like the flexible robot, there is no encoder, there is no sensor. Even scientists like the developed a bunch of sensor, not really good. Let's see the like the one example. Here. So do you remember like I explained the strain gauge, right? So there also like the some not strain gauge. However, this FPG, the fiber break grating, this sensor can really measure tiny deformation. Okay, so meaning is here on the core, this is like some elastic material, and then they mounted bunch of this FPG. So every like here on this is a section like the views, and then they mounted 3. Then each FPG measure the vertical, this longitude, like the one direction deformation. Okay, so then here, for example, when like this elastic core, this elastic materials anyway, like something bend, in this case, and you can see here FPG is anyway contracted. This is anyway the initial, and this is anyway expand. Somehow, using this contraction or expansion information, you can roughly measure deformation of each section, kind of. So here, from this 3, and then you can measure some angle, okay? And also here, 3 FPG, also you can measuring some, relative orientation. Here, also you can find some roughly orientation. Then, eventually, each orientation matrix, and then eventually you multiply the whole this orientation matrix to reconstruct the shape of this like the flexible manipulator. But the problem is this is a really, really amazing. What is the problem is that? Too expensive. Let's see. If you attach to this 8 unit, 1, 2, 3, 4, 5, 6, 7, 8, sensor cost is going to be 3,000 pounds, meaning is that euro is maybe 3,500 euro. And then we're using anyway here, serially connected 1, 2, 3, 4, 5, 6, 7, 8. That is a 3,500 euro multiplied 3. Then sensor price is going to be 10,500 euro. And also here, now we need to read all this sensor deformation information. We normally call these devices, which can read each of this FPG the deformation data. We call this is an interrogator. How much is this one? This is 25,000 euro. 25,000 euro plus 10,500 euro. If you want to make any medical device, then you need to pay more than maybe including the original cost and then plus manufacturing cost, and then maybe you need to pay, for example, this surgical instrument tool maybe cost 60,000 euro. Can you imagine how the government can pay all these 60,000 euro? That's the reason. And also, this is also I can tell this one. To mount it, attach all this FPG to this elastic material, also you have to attest manually. But for example, you successfully mounted 7, but 1 was a fail. Then you have to remove all. Why? Because I thought A sensor serially all the connected. For that reason, one sensor anyway the broken, then you have to change the all. So this is the reason like this is not really good. That's the reason. I also like to design some shape sensors, some very easy way. So now see here, there's some 2 unit, and then these 2 units also connected by the spherical joint. So then you can see here, spherical joint, and then this is by the top unit and bottom units anyway. And then we mounted 3 optoelectronic sensor. This optoelectronic sensor can measure 3 displacement, distance, right? So then somehow, now this upper unit is anyway rotating at the times, and then 3 optoelectronic sensor can measure distance. The 3 distance can also estimate 3 angle, pitch and rho and yaw, okay? But however, we are not gonna measure yaw. This is why we anyway using the 3 spring constrain the yaw motion. For that reason, now the 3 optoelectronic sensor can measure pitch and rho. And then now here 2 unit can measure 1 orientation matrix. This is between 2, 1 orientation matrix. Then you have already know the rigid link model, right? Once you know the orientation matrix, and then we put together, and then eventually we can reconstruct shape of this flexible manipulator. Then now see here. This is the first prototype. Oh my God. I mean, I don't really like this first prototype. Why? Can you see here? All the wire. Each unit, we used anyway 3 optoelectronic sensor. 3, and then can you imagine a bunch of this wire? How can we using this the prototype for actual surgical manipulator? Impossible, right? Yeah. So for that reason, we moved to we remove all this electrical wire cable. So then somehow, okay, we used this flexible circuit, right? Flexible PCB, okay? And then you can see here, this one is a optoelectronic sensor, 2, and then here. Now this is one link, okay? And this is another link, okay? At the times and then we used this convex shape reflector. And then now these 2 optoelectronic sensor can measure distance between this convex reflector and here. This is anyway the optoelectronic sensor. And then now when this the 1 unit anyway rotate at the times and then these 2 optoelectronic sensor can measuring distance, 2 point, and eventually these 2 unit can measure each relative the orientation matrix, right? So then here 1 orientation matrix, second, third, and fourth one, and then eventually we multiply each of these the orientation matrix, and then you can measuring shape. But here's a novel idea is that before in 1-dimensional the shape sensor, we used some various the radius, right? The radius anyway changes, right? So here then in 3-dimensional the shapes, and then we used convex shape reflector, okay? This is somehow the really noble, but still it only have a 4 the unit. So somehow we really wanted to making a little bit smaller diameter and then more longer, okay? But this is anyway right after this second prototype, and then here. So this is anyway demonstration video, but it's not really bad. And then this is a last version, okay? So here's an end. This flexible manipulator consists of the 2 segments. Each segment consists of the 6 the unit. And then now see here, each unit need 2 optoelectronic sensors to measure this relative orientation matrix, okay? So exactly the concept is the same, but however, we anyway increasing the 4 unit to 6 unit, and then now the 2 segment. So it's 2 segment. And then here, this is a demonstration video here. Just imagine like the here, optoelectronic sensor, optoelectronic sensor, optoelectronic sensor, optoelectronic sensor, optoelectronic sensor. So orientation matrix, orientation matrix, orientation matrix, and then this is a all like the multiply like the each of orientation matrix to reconstruct the shape of this flexible manipulator. This is a very new work. None of them really tried in this way for the shape sensing. The most of them used the conventional way. So this is this one. This work is around 20 years ago, and then 20 years ago, and then scientists started this idea using some FPG, which is can measuring the tiny deformation of any mechanical structure. But it is good. But here's and then also the main problem is that expensive. Okay, but another like the problem is that the sampling rate is now really faster. The sampling rate means for example, I know that like the surgical like the robot is doesn't really need like the fastest like the frequency. But however, the FPG itself, the maximum like the frequency input frequency is roughly 20 hertz or 30 hertz. It's a very very slower. But my one is basically I'm using the optical sensor. For that reason, actually, the maximum like the frequencies are more than 10 kilohertz. So meaning is much faster. Okay, this is like the one advantage. But anyway, here's what I really wanted to say is that none of them like the design some any shape sensor like the using this optoelectronic sensor. Okay, this is somehow my really noble idea in the world. I'm the first. Okay, and then here, something like you can see here. Now this version like we can just see the shape of the flexible manipulator at the times, and then still their arrow. Now here estimate blue graph, and then the red one is anyway actual like the shape, and then there's some tiny arrow, but however not really bad. I mean, to be honest, like in comparison with like the conventional like the shape sensor using FPGAs, and then my one is also not really bad. But the biggest problem is that still the most of like the medical devices the diameter should be smaller than 10 milli. But my shape sensor is currently like the diameter of this flexible manipulator. This flexible manipulator is roughly 22 milli. So still, I have to really work hard to really miniaturize this shape sensor. How I can just really implement some surgical manipulator like within 10 milli diameter. That is like my one challenge. So here, benefit, low cost, and easily integrate into robot structure. Why? Because you see here. Yeah, using like you attach the flexible circuit to the flexible like the manipulators, and that's all. Okay. So easy like the fabrication. So somehow we can produce manufacturing in mass production, and then noise level is very lower, and then faster frequency, like the response exceeding 10 kilohertz. Limitation, miniaturization. Still, we only can implement so many 22 milli diameter flexible manipulator, but actual medical devices should be smaller than 10 milli. Ongoing work. Actually, now I'm just anyway challenging. To measuring the 2-degree freedom, I use 2 optoelectronic sensor, right? But I'm using now the 1 to also estimate 2 angle using machine learning. Using machine learning is possible, but without machine learning, it's impossible. Okay, and also there's some hint. You little bit change the surface shape. Okay, because I used anyway some concave shape. However, we can't using that same shape. we have to change it a little bit different shape, but one sensor and machine learning can also estimate two angle. Then eventually, maybe size is going to be maybe reduced up to maybe 15 milli, okay? And also now another like the world scientists also are suffering, you know, like the soft robot, soft manipulator here. Before I end on my like the presentation, and then this is a biggest issue in like the robotics world. This one, this soft robot. Robot itself consists of the soft material, silicon. Okay, this is a still shape, detecting shape is one of the challenges. No one developed it, perfect shape measurement shape sensor, nobody. No. So now I'm just also working on shape sensor using optoelectronic sensor. It is working. I think anyone who like to participate in ICRA 2027 in Korea, at the times and then I'm going to present my work there. But at the times, I really hope you guys just anyway participate in the ICRA 2027. Yeah. So any question?
The question?
Yeah.
Are any of these sensors being manufactured?
This one?
No, I mean any of those. Yeah, if there's a company making them and they're being sold, or all are just prototypes.
Only this one. This is a like actually this is anyway selling, and then this sensor, all the sensor we used this one, cantilever beam one, this one. So not exactly the same shape, however, we a little bit modify, but actually the principle is the same. And then 43 sensors are integrated into this patient robot here. And this one, and this. This is selling everywhere. And then here also we're using this sensor to the measurement torque for the impedance control. So if you zoom here, like the, you see the like here. This is basically we integrated all our one force sensor, my design force sensor, into every like the robot joint, and then now this also like the impedance control. So impedance control is implemented into this patient robot system, but there isn't somehow it behavior looks like the robot has actual muscle. So like basically before injecting anesthetic, the robot joint is very stiff. So you cannot easily rotate like the tongue or head. But after the medical doctor injected anesthetic, and then suddenly the impedance coefficient will be lower, and all the like joint will be very relaxed. That's the like the why like impedance control like is implemented into this robot system. So this is also like the robot is anyway used to. So might develop this force and like the torque sensor. Okay, and then here this one, for example, this one is I'm kind of now currently like the commercialized some of this sensor, and then I really want to spin out my one company to just really sell this one. Here's and then still like the accuracy is roughly 90%, but 90% is not really enough. This is why I need to like really improving some accuracy. So at least like if the accuracy is achieved to 95%, then maybe I can start this selling. So, but to be honest, the selling this product is not the really main reason. Once you like establish your one company, then you can apply the bunch of Innovate UK project or some industry project. You know what I'm saying? Because if I have anyway company, then I can submit like my company's name, to this like the research fund. Then somehow some quite possibilities is gonna be really higher. And then yeah, currently I'm quite testing like in my office now. So and also another issue is that reliability. So I have to test at least to 6 months, whether they're still the 6 months and then the sensor performance is always the same or not. But this is the most important. At least 1 or 2 years. And then somehow I can say, oh, my sensor is very stable. But I do not know actually. And then also I have to solve some temperature issue. This sensor is also slightly sensitive to the ambient temperature. For that reason, somehow I'm quite designing how to just really compensate this temperature. But most of the sensing unit, we have to anyway compensate all the temperature. There's any 100%, sensor which is really immune to temperature. For that reason, this is just common. Any other question?
You said that for the new approach you are using just one sensor per joint. Is that correct?
You mean just like the shape sensor? Yeah. So currently I use the shape sensor 2, right, to measure pitch and roll. However, now I'm going to using only one sensor. So meaning is each unit is gonna be only one plus machine learning. But here's an idea is that also we have to change the different shape.
Okay. My question is, are they in straight line or they are orthogonally placed in zigzag pattern across the joints?
I'm not sure, but however here, something you can see here, this is PCB, here, PCB, and then we mounted this PCB, we attached here, and then now this is anyway the link, okay? The link is anyway the fixed with this spherical joint. So this is why each unit has a 3-degree freedom. However, we used 3 spring to constrain the yaw motion. So each of unit anyway has a 2-degree freedom. Actually, using 2 sensors also we can estimate 3 orientation angle. But at the time also, we need to change the surface shape cross machine learning. And also remember, here's when you're using anyway this optoelectronic sensor, the most important thing is that you need to anyway constrain some joint. Let's see the 4 sensor case in. 4 sensor case in, I fixed 5-degree freedom. Only allow the 1 degree freedom. Okay? Because let's see if we using the 6 optoelectronic sensor, of course we can measuring the 6-degree freedom, but somehow we need to really design some mechanical structure which is really constrains some many degree freedom. Okay? Because the optoelectronic sensor is if some surface is angled, right? A little bit not really in parallels, and then if the surface is a little bit angled, in that case, and then single optoelectronic sensor cannot really estimate very accurate displacement or distance. But there is a multiple unit means somehow I'm thinking maybe distance is gonna be very accurate distance, maybe could be measured. This is one of my idea. But no matter how regarding the shape sensor in proportional to the number of optoelectronic sensor, then size is gonna be bigger. But there is now I'm just anyway approaching single unit and also a little bit change the surface shape and also machine learning, then possible. So somehow these works will be present in ICRA 2027, and also another one is a soft shape sensor. That is I'm not gonna using optoelectronic sensor, but I'm gonna using the similar optoelectronic the sensor, not like this type. Yeah. But really good thing is that most of the shape sensor, if you touch the manipulator, then even there's no actual the manipulator doesn't really change their shape. However, sensor value quite change it. But my sensor is never change it. It's very robust. So somehow all of my work is really targeted for the very the practical the product. This is what I really have worked on so far. Because no matter how do we do the research, but if we cannot sell this one, what is the point? That is really important. Any question? Yeah.
Let's imagine you finish your research in 2027, as you promised. And the other thing,
Oh no, because like
I know it's never ending. Research is never ending. But
no.
I'm just asking whether you can see any opportunities for the industrial robotics, because there are a lot of applications focusing on assembly, automated assembly, where we need a lot of force torque sensing and impedance control. And this is the question whether you are thinking about also some industrial applications.
Of course, it is like the practical, because I'm really like working on very practical application. So practical application also like involvement in this industry robot. To be honest, too, like I contact Shadow Robot. They didn't really like my sensor. This is why that they are using magnetic and Hall sensor based force and torque sensor. That's just the reason I'm also making the force and torque sensor using the magnet and Hall sensor. The magnet and Hall sensor is quite good, but I told you, very noisy. So we can't using this magnet and Hall sensor with actuator, because actuator also like produce a bunch of magnetic field. For that reason, like the sensor doesn't really guarantee very accurate force and torque. But I quite contact like the Shadow Robot before, but they rejected. No, we don't want to like using your way. That's the reason I was very angry. This is the reason I have to show the 95% guarantee. Oh my God, don't say this too. Yeah, because normally they really want to see the accuracy, because they really want me to compare my sensor with the American company, like the ATI one. So I think that I can achieve the 95%, but that is not really a big issue. Another issue is that when I'm using this sensor for 1 year, 2 years, and at the times, then my sensor can really guarantee the same performance or not. That is a totally different, different thing. Because the LED and phototransistor, I'm 100% sure that their power may be degrade. You know what I'm saying? Just imagine like the LEDs always emit the bunch of light, like the 1 day, 2 day, no, 365 days in factory. The factory is always like manufacturing robot is working 24 days in 7 weeks. In this case, and then I'm still wondering whether this LED and phototransistor always show the same performance or not. Who knows, like suddenly power level is suddenly decreased, or maybe light intensity power is maybe decreased, right? In that case, and then I do not know. How can I just really like the repair, or do we have to recalibrate this sensor again? And this is all. Actually, only the strain gauge-based force and torque sensor has been verified. That's the reason in most of the industries and in like companies using the strain gauge-based force and torque sensor because of the reliability. Yeah. So this is a really it's just same. I mean, no matter how do you develop this medical device, if you do not test it clinically within like the 10,000 patient, we can't sell this one. Same. So once I make this one, then like I'm giving this sensor to the one of like the Brunel, the manufacturing. The guys are working on manufacturing, and then they mounted my sensor to the manufacturing tool, and then they're gonna like using 1 month, and after then I test it whether the sensor performance is still same or not, kind of this way. At least 1 or 2 years, and then I can say this to any company. No, 2 years and it was okay. The meaning is that you have to change my sensor every 2 years, kind of. Yeah, because of like I don't think I'm gonna using this sensor for like patient. Why? Because it's very dangerous. Yeah. So this is remember, this is why I designed patient robot, not like the medical device. Medical devices if there's some accident, I think that my previous companies will be over. Yeah. But patient robot is nothing happened. It's just robot. Okay. No matter how we like used, like maybe some component is broken and we can repair. That's all. Yeah. So any question?
Do I understand correctly that there is no initial calibration?
No, we have to do calibration, of course. Calibration is our most hardest part, actually. But here's something I can tell you funny thing is that these days, the most of the calibration is done by robot arm. So this one is a little bit different. The shape sensor one is slightly different. However, the force torque sensor case, and then like the using robot arms, and then like that there's a way to calibrate automatically. But shape sensor case, and then I can show you. It's a really stupid way. However, now see here. First, anyway, we fixed 1, 2, 3 unit. Okay, fixing the 3 unit, and then only we allow the top, like the unit is rotate. And then now we put this one. This is an IMU sensor. So then now 3 is anyway the fixed, and we regard it, the 3 units and as a rigid structure, and then solely 1 is anyway like the moving, rotating, and then now we can get IMU data, and then this pitch and roll data, and then we anyway can calibrate just 1 unit, and then after that, now we fix these 2, and also we fixed another 2, and then allowing this unit like to rotate, and then we mount it on the top this IMU, and then also same IMU sensor can get like the orientation, like the information, and then also at the same time the 2 optoelectronic sensor can detect it, all of this data, and then eventually we can also making the calibration metrics. The meaning is that every relative 2 unit has a 1 calibration metrics, and then these 2 also there are some calibration metrics, and then this is a 3rd calibration metrics. And then each calibration metrics is just orientation metrics. So then we anyway multiply this 1, 2, 3, and we can anyway calculate shape and also like the tip position. Okay, but force sensor, like the force sensor case, and then using robot arms, and then like that there's a way to easily calibrate like automatically like the calibration. So this is much easier. Yeah, but not only me, but also like the most of like for example we mounted force sensor, and then we put some calibration device, and then we put some load. Okay, something load, and then is there any pen here? Okay, any choke? Any choke? Here. So very easy way is that robot arm, and then this is my sensor, and then something we mounted this kind of thing. Okay, and then here we put weight, and then we fix this, and then now so there's many point, not only this point. And then now robot arm is we anyway mounted, for example, here, then maybe like maybe 200 gram, for example. The robot arm is have a variable this motion. So then at the times, and then we can also like get the orientation, right? At the time, we know like that is a gravity direction. From this gravity direction, we can something here. Moment is this force anyway. These ranks, and then something older we can do automatically. But once we finish this one, and then we also mount it here to here, here to here, and then like each of all this calibration has to be done. Like in this case, and then like we will get a lot of data, and then using MATLAB or Python, and then we can calculate calibration metrics. Right? Yeah. So this is a quite like I don't think these days. Like ATI sensor company, they're using the very conventional way. Conventional way is that sensor, then they pull the wire, and then here they put load. Like you understand something, and then sometimes and then they pull this way, and then you just anyway put the load, and then very like the old way. But most of like the European company, the low cost one is using this way. Why? This is takes like maybe 10 hours, but this is only 1 hour. Or more than 10 hours, I mean maybe 20 or 30 hours. Why? The ATI sensor, once you anyway like the purchase this one, when they started fabricating the sensor, it takes 3 to 6 months. For that reason, company fabricate in advance a lot, and then they just sell. But however, actually, when they fabricate sensor, it takes a minimum 3 months to 6 months. But European version one is a very simple concept. This is why all the massive production one. Yeah. I think yeah, thank you so much.
Thank you.
Thank you.